So we've been talking about carbons as asymmetric centers, an atom with 4 different groups. But any atom with 4 different groups can be an asymmetric center. So nitrogen and phosphorus that can be bonded to 4 different groups can also be asymmetric centers. So showing here, we have a nitrogen bonded to a methyl, an ethyl, and a propyl. Remember how to name these quaternary amines. You list the substituents in alphabetical order. You end the first name with ammonium, and then you write the counter ion, which in this case is bromide. So this would be ethyl methylpropyl ammonium bromide. But because it has a specific configuration, we need to list that at the beginning of the name. And to designate what is the asymmetric center, we would write N. So then instead of a number, we have N and as the location. Okay, so priority of groups. 3 carbons is better than 2 carbons, is better than methyl, which is better than hydrogen, number 4. As we go from 1 to 2 and 2 to 3, that is counterclockwise. So the first nitrogen on the left molecule is S, and we need to put the location of what is S. So I'm going to say NS, ethyl methyl propyl ammonium bromide. At the nitrogen, the configuration is S, and it's ethyl methyl propyl ammonium bromide. That means that this is R, and that would be R, NR, ethyl methyl propyl ammonium bromide. So that R is the stereoisomer at the nitrogen. You have to indicate where that stereocenter is located. If it's not at a carbon number, then you have to write what the heteroatom that is asymmetric is. For the phosphorus, it has 4 different groups, and it can also be labeled as an R or S configuration. We are not going to cover naming of these phosphate molecules, the phosphoester molecule, but we can list whether it's R or S. Oxygen would have the highest priority, followed by the ethoxy, CH3CH2O, followed by the OCH3 group, and then hydrogen. So going from 1 to 2 to 3 is counterclockwise. Yes, so this is S, and the enantiomer is R. This is simply so that you can be aware that when we defined asymmetric center, we defined it as any atom that has 4 different groups. So not only can carbon have 4 bonds to other things, nitrogen and phosphorus and some other atoms can have 4 bonds to other things. Amine inversion. We mentioned this at the beginning of the chapter as a configurational difference that did not result in a permanent difference. These molecules cannot be separated chemically. It's similar to, so just as we cannot separate molecules that differ in their conformation because of rotation of a single bond, we cannot separate amines that have inverted. What amine inversion is electron density of a lone pair of an sp3 atom spontaneously moving back into a p orbital and then inverting that sp3 orbital. So that the sp3 orbital at the far left is inverted compared to the sp3 orbital at the far right. That is amine inversion because these electrons, while in an sp3 hybrid orbital, that sp3 hybrid orbital can devolve back to a p orbital and then go back into an sp3 orbital. The lone pair does not count as a group attached to the nitrogen. We will only count other atoms as groups. A protein or an enzyme is a receptor of chiral molecules. I tried to explain this in the earlier slide. Our enzymes have what we call lock and key mechanism. They have a specific configuration of the substrate binding pocket that only certain shaped molecules fit into the pocket. So the R enantiomer can fit into the binding site because the atoms are in the right configuration. This fits perfectly, while the S enantiomer will not fit because it's the mirror image. So now the circle doesn't fit in the square and the square doesn't fit in the circle. The S enantiomer cannot bind this enzyme. It is not the key. Only the R enantiomer is the key. I have an example that I can give you about enzymes and enantiomers and medication. There was a drug given in the 1950s to treat nausea. It was given to women who were pregnant and expecting to combat morning sickness. One enantiomer of this drug was shown to have a positive effect in reducing morning sickness. However, the drug was not thoroughly tested. Upon ingestion, the body converted this drug to a mixture of the appropriate enantiomer and of the opposite enantiomer. So one enantiomer, while reducing morning sickness, was the desired molecule. But in vivo, your body converted it from the one enantiomer to a mixture of the S and R enantiomers. The undesired enantiomer caused severe birth defects, as illustrated by this child that has this very short arm. These children, many of these children were born with these birth defects. No legs, no arms, missing hands, conjoined twins as a result of this drug. And improper testing to ensure that only one enantiomer would exist when after taken by the patient. Now, all drug trials require that both the R and S enantiomers are tested for bodily effects and are thoroughly proven not to interconvert in vivo. A difference in enantiomers can either have a large effect or a small effect on certain properties. For example, R-carvone smells like spearmint, while S-carvone smells like caraway seeds. There's another example that we'll look at in OChem 2. We'll look at orange oil. The R enantiomer, one of the enantiomers of limonene smells like oranges, and the other enantiomer of limonene smells like lemons. I believe it's the R enantiomer that smells like oranges and the S enantiomer of limonene that smells like lemons. So they could be very similar as lemons and oranges, or different as spearmint and caraway seeds. And the reason that these molecules, while having the same general configuration smell different is because the receptor that binds the molecule, the enzyme that binds the molecule in the nose and gives a signal to our brain of what it smells like, is different because of the lock and key mechanism of enzyme fit. R-carvarone fits an enzyme that tells our brain that it smells like mint, and S-carvone fits an enzyme in our brain and fits an enzyme in our nose, and the nose sends a signal to the brain that says this smells like caraway. Physiological properties of enantiomers. Enantiomers can have, because enantiomers have different fits for lock and key mechanisms, they can have on their and which enzymes they bind, they can have very different physiological properties. As I was explaining with the drug thalidomide, where one enantiomer reduced morning sickness and the other enantiomer caused severe birth defects in the developing fetus. Another example of enantiomers having very different physiological properties because of the lock and key mechanism of enzyme receptors would be the active ingredient in Vicks vapor inhaler, menthol, versus its enantiomer, methamphetamine. I think you can very much agree with me that menthol in Vicks vapor inhaler has a very different effect than the drug methamphetamine. We've mentioned already that we can separate enantiomers, but how can we separate enantiomers? We separate enantiomers by converting them into salts. The crystals of the salts can be separated by a chiral material in a column and separated by chromatography. This would be one method of separating the enantiomers. The enantiomers also have a slightly different retention time by high performance liquid chromatography, or HPLC. We could separate them using this method as well. You are not expected to know what the methods for separating the enantiomers are.